Welcome to everyone who's joined me for this short talk as part of the Cambridge Zero Research Symposium. My name is Weinold, and I am going to share with you some of our results on the sources and impact of technology breakthroughs and process improvements, including the importance of knowledge spillovers in light-emitting diode manufacturing since the introduction of the first warm white diodes some 20 years ago. Our research is part of a larger project jointly undertaken by Harvard University and the University of Minnesota in the United States, as well as the University of Cambridge and ETH Zurich in Europe. The aim is to identify ways of accelerating innovation in clean energy technologies and formulate relevant recommendations for research and innovation policy based on a deep understanding of the drivers in innovation in existing energy technologies, including solid-state lighting on the demand side, solar photovoltaics on the supply side, and lithium-ion batteries on the storage side. The project is funded by the Alfred P. Sloan Foundation. The reason why we are interested in the evolution of light-emitting diode technology is simple. Some 25 years after the introduction of the first commercial white light-emitting diodes, and after legislation aimed at increasing the adoption of solid-state light sources has been implemented, the solid-state lighting industry has become a success story in the global drive for the transformation of energy systems. The general illumination market penetration in the US and the EU is exceeding 50%. As you can see here, legacy technology, such as the orange-tinted low-pressure sodium lamps, are being replaced by light-emitting diodes even in demanding applications such as outdoors lighting. Today, the solid-state lighting markets in the US and the EU together are valued at $58.7 billion. Estimates for the electrical energy saved annually from the adoption of solid-state lighting by 2020 range from 130 terawatt-hours per year for the EU to 442 terawatt-hours per year for the US, which, as you can see, is on the same order of magnitude as the amount of energy produced by all deployed solar photovoltaic installations in the European Union, and even higher in the US. This revolution in lighting has been enabled by dramatic improvements in overall device efficiency and reductions in manufacturing cost. The first warm white diodes introduced in 2002 exhibited overall efficiencies of below 6%, with a luminous efficacy of about 20 lumens per watt, while the highest performing devices today exhibit overall lamp efficiencies of above 38% at a luminous efficacy of about 240 lumens per watt. As you can see, no other lighting technology in the past 200 years has exhibited such large efficiency improvements in such short a time. In fact, light-emitting diodes are nearing the physical efficiency limit for the conversion of electrical energy into light. As the inset plot shows, this high efficiency means that even early diode-based lamps were more economical than legacy technologies. Despite this, the underlying drivers of efficiency improvements and cost reductions are poorly understood, partly because of the proprietary nature of research data in the field. This is why this project aims to understanding the pace and underlying drivers of innovation in phosphor-converted, warm white light-emitting diodes between their introduction and today. In particular, we're interested in identifying sources and compute the effect of technological improvements and knowledge spillovers. We used a multi-method approach to gather data on device performance, identify knowledge spillovers, and compute their effect on relevant device metrics. We combined a systematic literature review of scientific literature, industry reports, technical periodicals, and patents with a bottom-up manufacturing cost model for different diode architectures and years, performance simulations performed in Python, and finally, interviews with eminent experts in academia, industry, and government research institutions. This approach was necessitated by the availability of data in a sector that is dominated by research in private companies who naturally seek to maintain a close guard over their data. Before I can present the results of our study, I must briefly discuss the metrics we used to quantify technological progress in light-emitting diodes. Improvements in overall device performance are best described by device sub-efficiencies, each corresponding to a separate loss channel of a different underlying loss mechanism. While a discussion of these effects would be beyond the scope of this seminar, the important point is that many different loss channels exist within the device. Some decrease electrical efficiency, some optical efficiency. As a single example, the first blue channel here, unextracted light, corresponds to the light extraction efficiency. It describes how many photons are reabsorbed within the device after they are generated. An efficiency of 100% means that all light can successfully leave the device. All these sub-efficiencies were used to quantify technological breakthroughs in devices. They allow us to capture single changes in chip architecture or manufacturing processes. We found that we also needed to consider a number of consumer experience metrics, describing the quality of light emitted by diodes. There are many such metrics related to lighting, However, the two most relevant include the color temperature of white light and the ability of a light source to faithfully render colors. You are surely familiar with this first metric, which describes the perceived warmth or coolness of white light. The higher the color temperature, the cooler the light source appears. General illumination at home usually tries to imitate color temperatures close to those of incandescent bulbs in the warm regime. You can see here that the color temperature of 1997 diodes and the improvements that came with a 2004 breakthrough which enabled warm white light from light-emitting diodes. The second consumer experience metric is the color rendering index. It describes the degree to which a light source renders colored objects in a similar way to illumination under sunlight. A low color rendering index, from early fluorescent lamps for example, made saturated red colors look washed out or faded. A simulation of the color rendering performance of different light sources has been performed and is shown here. Perhaps you can see the visible difference in saturation of the red strawberries in the top row. To illustrate our method, I can show how we determined the historical improvements in the spectral efficiency sub-efficiency. Spectral efficiency describes the spectrum of light which is generated by the phosphors surrounding the blue LED chip. Raw spectral data, as is shown here with black curves, is reported in scientific publications and device datasheets. However, the type of phosphor compound used in these devices corresponding to the datasheets cannot be determined. The associated spectral efficiency is also not reported in these datasheets. We thus gathered data on the specific phosphors used in different devices from expert interviews. By combining data gathered in similar ways for all other sub-efficiencies, we were able to gain a deep understanding of the evolution of the technology. Each column here corresponds to one of the sub-efficiencies we considered. SE, for instance, corresponds to the spectral efficiency discussed earlier. Total lamp efficiency here is eta P. We found that the lamp efficiency for the highest performing devices at a test current of 350 mA has increased from 6 to 38% between 2002 and 2020. Improvements have been made across the entire range of device sub-efficiencies, shown here. Colored horizontal bars give the levels of best performing devices for different years. Note that levels for devices in 1997 are shown here only as additional sources of reference for the internal quantum efficiency and the light extraction efficiency, IQE and LEE. Other sub-efficiencies do not have data for years before 2002, as either red phosphors were not yet used in down conversion, or the electrical current did not reach the 350 mA used in later devices. The approximate physical limit for the sub-efficiencies are shown as black horizontal bars at the top of each column. In total, spillovers, here colored blue, have contributed 8.5 of total efficiency improvements. Keeping in mind, however, the consumer experience dimension, we go on to this figure, a first attempt at showing the impact of knowledge spillovers onto consumer experience metrics. On the x-axis, we've got the color rendering index, where for the sake of simplicity, we assume that higher is better. On the y-axis, we have color temperature, the perceived warmth. Here, for home lighting, we assume that values in the range of incandescent lamps are desirable. We can conclude that spillovers were responsible for nearly 100% of improvements in consumer experience, including the enabling breakthrough of warm white light-emitting diodes. 3 data points for CFL, compact fluorescent light bulbs, have been added for reference. Using our cost model, we estimate that the cost of manufacturing low to mid-power light-emitting diode packages at a US location using state-of-the-art equipment have declined from $1.11 in 2002 to only 5 cents in 2020, a 95.5 overall cost reduction. All currency is in 2020 dollars. Our preliminary results on the sources of cost reductions show that the largest contributor to decreasing manufacturing costs is an increase in the size of the wafers used to grow the light-emitting diode chips. It's important to note that this applies only to our model of a factory employing the best possible equipment available at the time. Manufacturers today continue to operate lines with wafer diameters smaller than those assumed in our model. The main plot here shows the relative contribution of different parts of the manufacturing process to total cost. As is evident, given the best possible equipment, packaging the devices has become the biggest contributor to cost at nearly 60% of total manufacturing cost, up from only 7% in 2002. This is mostly due to an increase in the size of the wafers used to grow the diodes, and the inset plot here shows how the number of chips per wafer increases as the wafer size increases over time. In conclusion, in our work we found that lamp efficiency for highest performing commercial devices has increased from 6 to 38% from 2002 to 2020. Among the ensemble of loss channels responsible for losses within the device, no single channel is dominant. Manufacturing costs have dropped from $1.11 to only 5 cents from 2002 to 2020. This has been primarily the result of a move to larger wafer diameters. The largest contributor to total cost, according to estimates from our model, is chip packaging at 60%. Knowledge spillovers are responsible for nearly 100% of improvements in consumer experience metrics. In summary, improvements in those sub-efficiencies associated with loss channels with a good physical understanding of the underlying mechanisms have come primarily from targeted technological breakthroughs. Spillovers are also more likely to occur in these well-understood areas. On the other hand, improvements in sub-efficiencies associated with loss channels with a poor physical understanding of the underlying mechanisms have come from the manufacturing process improvements associated with these sub-efficiencies. Our results further show both the importance of basic research itself and the level to which applied research relies on knowledge flow from basic research. This reinforces arguments made against the dichotomy of basic research versus applied research. As a conclusion, our results show the importance of further research into the underlying solid-state physics of light-emitting diodes. A deeper physical understanding of the underlying effects and mechanisms associated with device loss channels will enable further technological breakthroughs to improve efficiency. With that, I would like to thank you for your attention. You can follow our research by subscribing to our Twitter accounts.